I'm Raven, and welcome back to Galactica. In this video we're going to be taking a general look at the electronics inside the model. I've got all the components, so let's get going. Just as with Voyager, Battlestar Galactica is going to be completely lit up. I've looked at some lighting references for Galactica, and I've decided I'm going to light up the main front of the ship where there are some windows, the two hangar pods, the two interiors of the hangar pods, and the engines. As I mentioned in the introduction video, I want the LED strips on Galactica to be dimmer than they were on Voyager. And as you can see here from this fully lit up prototype, and don't worry, this looks pretty crazy, but I'll be explaining it in gross detail, I've managed to accomplish what I believe will be just the right level of brightness for the various components. Let's take a look at what I'm going to be doing first. Starting off, I'm going to require 5 LEDs for the engine components. Now the engines need to be a very specific color of blue turquoise. It's not really white, it's not really cool white either. It needs to be a more of a... It has to be definitely blue, but on the white side of blue, but with just that hint of green to it. So I'm going to use RGB LEDs so I can configure that exact color that I want. And I'll be showing you how I did that in a moment. So in each of the engine pods, we're going to require a small board with 3 resistors. Each resistor determines the amount of current going into the LED, which determines how bright the red, blue, and green diodes are. And then we'll need 5 of these that then link back into the main body. In the rear of the ship will be a sub-board where all 5 of the components will simply link up, which then goes off to the main board. I've iterated the main board a couple of times, but as is the way of Occam's razor, it's just going to be 3 very simple strips, one of which will be running at 12 volts, a common ground, and one that will be running at 8 volts. Now the 8 volts is the brightness of the LED tape that I'm going to be using. It's still 12 volt tape, but when running at 8 volts, it's at just the right level of brightness. To achieve that 8 volts, you could do things like pulse width modulation, but in this case I'm going to use a voltage regulator, which takes it from 12 down to 8. It's a very simple, neat solution, which I'll show you in a moment. Connected to that's the LED tape. There'll be 5 separate strips that come down into the board, and the whole thing just plugs together, much like with Voyager, where there was the central board inside the engineering hull that all the components simply jacked into. In Galactica's case, there's not quite as much space for having a control board with the spade connectors, so the whole thing will need to be connected together and soldered directly to the boards, because there's just no space for those spade connectors. So let's come over and look at what I've got physically going on here. This is the fully laid out board. I've got all the LED strips, all the engine LEDs, every single component required for the build. These LEDs are just behind a piece of tissue so that I don't blind you with their raw intensity. We'll start off down here. The circuits will come in at 12 volts and then go through this voltage regulator. The 12 volts will then further go onto the LEDs, but with this voltage regulator it outputs 8 volts on its 3rd pin. This allows us to have the LED tape running at this far lower brightness. For example, if I take one of these pieces of LED tape and run it at 12 volts, that is the difference in the level of brightness we're talking about. I used a bench power supply to play around with the voltage until I reached a level that I was happy with, and I decided that 8 volts was dim enough that it had that nice, calm Galactica feel to it, while still being bright enough that it should light up the model. So all of the LED strips will come off the 8 volt channel of this voltage regulator. The 12 volts will continue as normal to the RGB LEDs. RGB LEDs are essentially 3 LEDs in one container, a red, a blue, and a green, RGB. In order to determine the color, you just change the amount of voltage going into each LED, making them brighter or dimmer. Which is why we have here 3 resistors and 1 ground going into each LED. By increasing and decreasing the amount of resistance, you can change the color toward red, toward blue, toward green, until you finally get to a color that you desire. One mistake I've made at this stage that I will note is I bought clear RGB LEDs. And the trouble here is that you can see the individual colours. Here you can see green at the top of my hand and blue at the bottom. Because inside, it is just 3 separate LEDs. If I had bought diffuse LEDs, then it would come out at the correct colour. If I place this tissue back over it to diffuse the light, you'll note that it comes out as that actual blue colour that I desire. And that really is it as far as the electrics go. There's no 555 timer, strobes, or anything along those lines. There'll be more specific videos as we actually implement each stage. For example, with these engine LEDs, they're going to have to be mounted inside the engine pods, which will mean cutting a couple of the pins out of the pods. The last thing I'm going to talk about in this video is how you figure out what color you want these LEDs to be, because it's not very simple to work out the actual values. As some of you may well know, red, green and blue work on a scale of 0 to 255, where 0 is black and 255 is pure white. And you get different shades of colors by increasing and decreasing the lightness of each shade. Pure red, for example, is 255 with no green or blue, and as we shift through the hues, the lightness of each color in turn increases and decreases, giving you the various shades of pure colors. Pure white is a maximum mix of every single color at maximum brightness. The question is, how do we turn this 0 to 255 scale into something that you can use with a resistor? The first step is to find the color that you want. I settled on a light egg blue for Galactica's engines, which is a red value of 186, green 223, and blue 243. So, mostly blue, a lot of green, but far less red. So how do we turn this into a resistor scale? We're going to have to do some math, I'm afraid. We'll need to know a few things before we can figure it out. For example, we'll need to know our source, which is a 12 volt 2 amp adapter, the statistics of our LED, its minimum operating voltage, maximum operating voltage, and its draw in milliamps. And you need to figure out what the smallest resistor is you can use. Thus, calculating the minimum amount of resistance that you need is the standard calculation of taking the voltage and dividing that by the draw. That gives you the smallest level of resistance you need to apply in order for the LED not to pop. So again, you may ask, how does this help? We know that RGB operates on a scale of 0 to 255, where 255 is white. With resistance, we know that the minimum amount of resistance required is maximum brightness. So in turn, we need to apply more resistance to dim the LED. Now you're never going to really find a resistor that will cause the LED to be off completely. Even at 1 million ohms, the RGB LED was still lighting up very, very slightly. The idea is to find a level of resistance where it will not affect the color of the mix, and you can treat that as if it were off. I've picked 9000 ohms. It's an arbitrary value that I've got through experimentation. You may find that your values are slightly different. But we now have a scale of 490 to 9000, much that we have the scale from 0 to 255. Here's where the magic happens. If we take the maximum value of the RGB scale, 255, and divide that by 100, we know that 1% brightness is equal to 2.55. So by dividing our RGB values by that 2.55 value, we can see that we need to have the red channel at 73% brightness, the green channel at 87% brightness, and the blue channel at 95% brightness. Using our resistance calculations, we can do the same thing. We know that 490 needs to be treated as maximum brightness and 9000 as our minimum brightness, which gives us a range of somewhere around 8510 ohms, which is simply subtracting the minimum from the maximum. We can then divide this value by 100 to see that for every percentage point of brightness, we need 85 ohms taken off the maximum. And note that it's taken off the maximum. The resistance needs to go down to increase brightness, whereas the RGB scale goes up to increase brightness.
So by multiplying that 85.1 by 73, we get 6,207 ohms. Minus that from the 9,000 value, and you can see that we need a 2K7 resistor to achieve 73% brightness. It's worth noting that the red channel uses a different voltage to the green and blue channels. You'll need to take this into account, especially when it comes to your minimum, as they'll be running at different voltages. I've used 9,000 as my maximum for all of them, but you may need to play around with that value if you're trying to be far tighter. In total, to get my RGB value of 186.223.243, I need a 2K7 resistor, a 1K5 resistor, and an 800 ohm resistor. You'll need to round up or down to find the nearest standard value resistor to what you're looking for, as it'll be extremely unlikely that you will find a 2793 ohm resistor unless you make one yourself.
Well, that's going to do it for this video, however. More than enough about electronics for one session. I've put a copy of my RGB calculator, or a Google Docs version, in the description below, so if you're looking to work out some calculations or see how I did it, check that out. In the next video, we're going to start looking at the hangar pods. It's a tie between engines and hangar, but I decided the hangar is going to be far more interesting to get going. But until then, I'm Raven, and that's all from Galactica.